Yeah, hi everyone. So I was recently putting together some slides for an in-person event, a 20-minute in-person event, and I thought it might be interesting to just record to see if it's indeed 20 minutes. So in this talk, I want to talk about the LLM landscape in 2025, like what are the major LLMs out there and what are some of the interesting alternatives that are currently emerging and what my thoughts are on these alternatives. So I will start with the LLM main track in 2025. So with main track, I mean like the transformer-based, state-of-the-art open weight models that, let's say, are most widely used right now. So for example, from DeepSeek version 3 to GLM 4.6. And then in the lower right corner, also some recent alternatives, or I wouldn't say alternatives, but recent flavors of these models, for example, Gwen 3 Next and DeepSeek version 3.2, which have a few tweaks I want to briefly also talk about later. But for now, let's just focus on the main track. And one of the themes this year has been on making the models bigger. For example, starting with DeepSeek version 3, which was about 600 billion parameters, and then Kimi K2 with a trillion parameters and so forth. So that was one of the themes. But more importantly, with making these models bigger, the other theme was lowering the inference requirements so that actually people can run them in an efficient way. I mean, it doesn't necessarily mean we can run them at home on a laptop or something, but at least also in a data center that it's kind of feasible to run those models at scale and not losing too much money, let's say. So one of the themes is lower inference requirements. And so there have been a few tricks over the last few years to make the inference requirements a bit lower than they were before with multi-head attention. So one of the tricks was grouped query attention. And it's not a new trick or anything. It's been around for a long time. For example, even back in 2023, Llama 2 used grouped query attention in the larger models. So it's nothing new, but it's a very popular trick. So here on this slide, there are a few models. This is not an exhaustive list. So there are a few models using grouped query attention from Gemma 3 to GLM 4.6. And so grouped query attention is not the focus of this talk, but it's just like a mild, slow introduction to some other variants later. So grouped query attention is essentially replacing the multi-head attention module in an LLM. So it sits inside the transformer block, and the transformer block is repeated a number of times. Here I'm just choosing Qwen 3 because it's just such a popular model. So the grouped query attention, what it does and how it differs from regular multi-head attention is it's defining these query groups. So on the left-hand side is the traditional multi-head attention mechanism, where for each query, for each input, we have a key and a value. And then in grouped query attention on the right-hand side, we now have these query groups. So here I chose an example where we have also 6 queries still, like the heads, query heads, and then 2 query heads share the same key and value. So in a sense, we are sharing things. So that means we have fewer keys and values, and having fewer keys and values means that the KV cache, that is nowadays really a requirement in inference to make it feasible, the KV cache will be much smaller because we have fewer things to store here. So if we look at the left-hand side, we have 6 values and 6 keys. On the right-hand side, we have 3 keys and 3 values. So we have essentially reduced the KV cache size by a factor of 2 in that sense. So so this is one of the tricks. Of course, we can take this to the extreme. We could, for example, make only one group, which means all the queries share the same key and value, but that would be too extreme. And by the way, this is called multi-query attention. And then the model starts, in terms of the accuracy, the modeling performance, it starts becoming worse. So we don't want to make it too extreme. It's a hyperparameter we have to tune, but if we find a reasonable let's say, ratio, how many keys and values are shared or how many queries share a key and value, then we can actually make sure that it is approximately the same modeling performance as with regular multi-head attention. So this has been around for a long time, one of the most popular tricks to reduce the KV cache size. Here's just an example where I plotted different KV group sizes. So going from the top, this is like the multi-head attention, the KV cache size in multi-head attention. And then going down, the more groups we use, as you can see there, the lower the total KV cache size. And so it's a hyperparameter how many groups we use, but with that we can kind of reduce the cost. That's one important trick in our tool belt today, basically. Interestingly, there was, of course, there's always new stuff coming out. This is not that new anymore, but I think it was 2024, DeepSeek version 2 introduced multi-head latent attention, and they also used it in DeepSeek version 3, which came out in December 2024. And then, of course, also DeepSeek R1, which came out earlier this year. And then Kimi K2. They use something called multi-head latent attention instead of grouped query attention. So what is multi-head latent attention? The reason why I spent so much time on grouped query attention is that this has a similar goal, but it's just a different implementation. It's we can technically combine it with grouped query attention. No one has done that yet, but it's technically combinable, or yeah, we can put them together. But most of the time here in DeepSeek and Kimi K2, this is a technique that is used instead of grouped query attention. And so how it works is on the upper right here, I have the regular multi-head attention module where we have an input token, and then we have the WQ, WK, and WV, which are the three weight matrices in the attention mechanism, which create the query key and value vectors. That's just the regular multi-head attention again. And so multi-head latent attention is introducing another, in total, another transformation here. So we go, instead of directly from the input to the keys and values, we go to a compressed state. So this is essentially a compressed latent representation of the input tokens. And so we use that for both the keys and the values. So in a sense, you can think of it as saving space by compressing it to a smaller representation. Store the compressed representation in the key and value caches. And then when we run inference on the next token, or in general, we up project it at each step. So we have two matrices to up project the shared latent representation into a key and a value. So it's kind of like LoRa. It's a bit lossy. So where we have another projection that downsamples and then a projection that upsamples instead of going to the key dimension directly. But that allows us to have this smaller KV cache, and that saves us essentially storage. And according to ablation studies in the DeepSeek version 2 paper, they found that this actually performs better than grouped query attention in terms of modeling performance. So it's a little trade-off compared to regular multi-head attention, but it's another way we can keep the KV cache size down. And here I have a chart again where we see multi-head attention at the top, and then different multi-head latent attention hyperparameter settings below that. So here I just changed the latent dimension. So the original embedding dimension here in this example is 2048. And so here we have smaller ones, for example, 1024, 512, 256, 64. So you can determine how big the latent dimension is, but the smaller we make it, let's say, the more of a trade-off this is. It's similar to increasing the groups in multi-query, in grouped query attention. And if I haven't done that here because it would be too crowded, if you would take this plot and overlay it with the other plot, the compression would basically match. So you would get the same rate of compression. But with multi-head latent attention, as the DeepSeek version 2 paper showed, you can get a bit better modeling performance. But it is also a bit more complicated to implement. Another trick is sliding window attention. And so this is not super popular anymore. Gemma 3 this year, I mean, only looking at models from this year, Gemma 3 used it. Mistral 3.1, I would say, kind of used it. It's a bit confusing. They had earlier Mistral models that did use sliding window attention, but if you go to the Hugging Face Model Hub and look at Mistral 3.1, sliding window attention is disabled by default, but then there's a GGUF version of it where it's enabled. So it's, I would say it's, you can use it, but I think it's not the default. Anyway, so what is sliding window attention? I added it here for completeness. So again, if we take a look at regular multi-head attention here on the left-hand side, so here I'm showing you the regular causal self-attention mask in single head in multi-head attention. And what we can see here is for each token, the token pays attention or attends to every token up to itself. So all the past tokens, that's the so-called causal attention mask. So it can't see future tokens. That's just the regular multi-head attention mask. Now, sliding window attention, what it does, it's limiting how far back a token can look. So here, picking the token 2, you can see it shows a window size of 3, so it can only look at itself and 2 previous tokens, so it can't see beyond that. And the idea is if we have a long context, this also saves compute or memory, more importantly, so for the KV cache, for example. So here we don't store everything, all the KV values in the past, we only store them up to a certain point. Again, if I'm plotting this, you can see there is a lot of KV cache savings on the y-axis. Again, that's the total KV cache size in gigabytes, and so lower is better. At the top, again, the multi-head attention, the regular one, and then the dotted line, the blue dotted line is a version of that where we use sliding window attention with multi-head attention. And we are using here a 5:1 ratio, which is similar to what Gemma 3 did. So the 5:1 ratio here means that we have 5 sliding window attention layers followed by a regular multi-head attention layer. Because remember, in the LLM, we have multiple transformer blocks. Let's say if we have 30 transformer blocks, the first 5 transformer blocks would be sliding window attention, then a regular multi-head attention, then another 5 sliding window attention layers, and so forth. And the idea to sprinkle in multi-head attention layers still is to have occasionally this full context. Because if we only had sliding window attention, we again would get a penalty in terms of modeling performance. But if you choose it with this 5:1 ratio, the Gemma 3 paper had actually a good ablation study showing that it doesn't really impact modeling performance that much. So there are 2 more entries here, the orange ones. So the solid orange line is grouped query attention with a group size of 4 for reference. And then the dotted version is sliding window attention with grouped query attention. So you can add sliding window attention on top of grouped query attention. And that is exactly what Gemma 3 is also doing. So you can combine them. And you could technically even use or add multi-head latent attention to it. But I am not aware of anyone doing that. So, but yeah, just as an example. So the bottom line is there are multiple ways we can reduce memory, and this year, I think, has been a year where almost everyone uses at least one of these techniques to lower the cost, the memory requirements in inference. Another trick is mixture of experts, and this is something almost everyone uses nowadays. So there are, of course, a few smaller model variants. For example, the Qwen 3.6, 4 billion, 8 billion models, they don't use mixture of experts. But if you go above a certain size, it just makes sense to use mixture of experts. And as you can see, almost everyone is using it. So what is mixture of experts? So on the left-hand side, we have an architecture without mixture of experts. By the way, this architecture doesn't exist. It's a DeepSeek version 3 type of architecture, but just for reference, I made it up because it doesn't have the mixture of experts. On the right-hand side, I'm drawing the same architecture now with the mixture of experts, and that is exactly what DeepSeek version 3 is. And so what mixture of experts is, it's replacing one of these feed-forward modules with multiple feed-forward modules on the right-hand side. So in this case, 256 feed-forward modules. The reason why we are doing it is this increases the total parameter count of the model, while only, let's say, increasing the inference cost by a little bit. Because in this case, we have 256 feed-forward modules. They are called the experts, but we are only using 9 of them in each inference pass. So there is a shared expert that is always activated plus 8 other ones. So we have 9 experts instead of 256 active. And that's why it's called sparse, because we don't use all of them. We only use a sparse or a small subset of them. And that saves us a lot of parameters in inference. So for example, this model is 671 billion parameters big. However, in a given token inference step, we only use 37 billion. The advantage of mixture of experts is it still has all these parameters during training, where the model can take up a lot of knowledge. But then in inference, we don't need all that knowledge. For example, when we have a math task, we don't need to, let's say, know about foreign languages, or we don't need to know about coding. So we can only use experts that are, let's say, good at math. It doesn't work quite like that because it's implicit in a sense how the router decides what to route for, or like what experts to use. But the training optimizes it in a sense that it is, let's say, not using all of the experts, only the 9, but then also using the most efficient ones for the given task. Yeah, and that is a mixture of experts, something everyone uses. This was a very quick overview because there are only so many minutes. But if you are interested, I have this article, The Big LLM Architecture Comparison, where I walk through all of them a bit more slowly and have also a few more other things that are interesting in terms of what the architectures today look like. So yeah, if you're interested, check out my blog. I wanted to briefly talk a bit about alternatives too here in this talk now. So far we covered the usual candidates, the popular LLMs that are open weight and that everyone is talking about. And I would say the advantages of those, I would personally, if I had to implement something, I would use those because they are proven and the tools for using them are pretty mature. The transformer architecture is pretty well understood in terms of the trade-offs, how to implement them, and so forth. They obey we have scaling laws. They obey all these scaling laws we have developed over the years. We know if we make them bigger, they perform better, and so forth. And they are, of course, state of the art. For example, GLM 4.6 right now is really on top of a lot of benchmarks. It's one of the best models out there. The downside, of course, is they are pretty big and are expensive to train. And even though we have all these tricks, inference is still pretty expensive. So people are developing these kind of alternatives. So for example, here are a few: Minimax, Gwen 3 Next, and DeepSeek version 3.2, where they have a few tweaks to them. For example, Gwen 3 has this gated delta net. DeepSeek version 3.2 has a sparse attention mechanism, like making things even more efficient compared to the tricks we have just seen. But again, they add more complexity, and also there's like a trade-off in terms of accuracy and modeling performance. So if you make things more efficient in terms of alternative, let's say cutting corners with alternative implementations like gated delta net and sparse attention, you may get a modeling performance hit in terms of how accurate the model is. If we go off the main track further, there's also, that's like currently the hot model, the tiny reasoning model, which is related to the hierarchical reasoning model. It is a very interesting new approach. They have been showing that this type of model performs very well on puzzles like Sudoku, maze pathfinding, and ARC, the ARC language benchmark, logical puzzle type of thing. However, it's not a text model. So it's kind of cool that people are working on that, but it's not like a model that you can chat with or ask questions. I think maybe one day there will be a module inside an LLM, like a function calling LLM, where an LLM can use a pre-trained small recursive transformer to solve a specific puzzle, for example. But they are not special, so they're not general purpose. They are special purpose models that have to be trained for a special task. So I would say they're cool, but they don't replace the decoder style transformers. I mean, they're themselves decoder style transformers, but they're not replacing the LLM decoder style transformers here at the top because they are very special purpose. We have code world models. And so world models in general have been mostly for vision tasks, but there was this code world model I saw earlier this year. And it's actually pretty cool. So they take the idea of transformer style LLMs a bit further. They train on code traces where the model kind of simulates how the code is executed and then knows about the internal variables of the code. So it kind of like understands a bit more about the environment, which I do think this is actually a really interesting, promising approach. It adds more complexity, of course, but yeah, I'm curious curious to see where that leads to, and I think we will see more of that also, like to take the next step beyond the current iteration of coding models. Text diffusion models are also quite popular. There are a lot of papers this year on text diffusion models. I mean, diffusion models have been around also mainly in vision. For example, Stable Diffusion made diffusion models pretty popular a few years ago. But for text, it's I would say it's a newer topic because text is discrete compared to continuous pixels. I mean, I tried a demo once. They perform pretty well and they are interesting, and I think they are definitely a contender for being useful. But I think that the downside here is also, I mean, there's the upside that we can have highly parallel generation because it generates everything at the same time and then refines it in iterations, like the denoising part, but for text. But it's not like how can I say it's different. So there are many applications where people want to see, like if you have especially a long let's say query and answer. Personally, I start reading the answer while it's being generated. This wouldn't work here because you have to wait until it's generated. You can see some the intermediate steps, but you can't really read from left to right the answer. The other thing is also I don't know if they benefit from the reasoning chain of thought type of approaches, especially relevant in coding, because it is kind of refining everything at the same time. I do think it's interesting, though. I think it's cool that people are working on it. I just don't know, let's say, in the era of reasoning models and agents, how that will factor in. But, I'm not an expert in diffusion model, text models, so we will see. It's just like something I find interesting. And liquid foundation models, again, I think it's a hot, interesting new approach. It's like it's based on differential equations, essentially. It's something that is very different from the decoder style transformers, but I must admit, I don't know too much about liquid foundation models in terms of have never used them, but they do look very parameter efficient, and I'm glad people are working on these types of alternatives. So I recently saw there is also a mixture of experts, so basically scaling up those models. So I'm curious where this will lead to. So again, I always appreciate it if people are working on alternatives. So that is another interesting direction. Transformer RNN hybrids. I also recently saw there is a new RWKV model out there. So it's essentially marrying transformers with RNNs. So far as I can tell, the accuracy on, like long reasoning chat type of tasks is still worse than for the models at the top. But it's again, it's cool that people are working on alternatives. So one advantage here is especially, I mean, I said it's worse on long context tasks in terms of the modeling performance, but it is much cheaper to work on long context tasks because based on my reading or my understanding is it's constant memory because it doesn't have a KV cache. It has this intermediate representation essentially, like an RNN, and it is essentially in that sense not getting more expensive the longer the context is. But then also, because everything is a latent representation, you do lose over time modeling accuracy because yeah, you can't compress infinite information into a latent space essentially. Yeah, and then Mamba state space model. State space models are also pretty popular. There are actually this year really cool models that are in the state space modeling space. So for example, I checked the LLM leaderboard. There's a Hunyan, I'm not sure if I pronounce it correctly, Hunyan T1 model. And top of my head, it was around somewhere on position between 20 and 30, which is actually pretty cool because it's also not a huge model. So these state space models are getting combined now with transformers because state space models themselves were not quite as good. They had too many limitations. So there are now these hybrids. And yeah, they are also they are getting better and better. So we have finally also models on the leaderboard. And then there's still also LSTMs. So there is the X-LSTM model, which is also still a thing. And I think one cool thing about it is back in the day when I studied, it was all RNNs and LSTMs for text. And it's, it's cool that they are still being refined because there's a lot of theory and understanding in that field. So it would be sad to lose all of that and to, still carry on this line of research, make the models better with today's insights. So it's I think it's the use case here is like for highly efficient models on devices and so forth. It's not like a GPT-5 type of big model that can do all kinds of things super well, but I can see for small on-device models how they are still being attractive. Anyway, so these were just my top of the head thoughts. I'm actually writing up all of that in a blog article. I don't know when it will come out. Maybe I will share this video shortly before it comes out. So maybe keep an eye out. And yeah, if you're interested to see if I had time to wrap up the article, and so you can check it out. Beyond that, I'm also working on a new book, Build a Reasoning Model from Scratch, which is essentially a continuation of Build a Large Language Model from Scratch. It starts with a pre-trained model and then implements reasoning-related techniques, inference techniques, and training techniques. And I thought if you liked my previous book, Build a Large Language Model from Scratch, this might be an interesting follow-up book I'm currently working on. With that, yeah, I think I am a bit over the 20 minutes I I previously mentioned, so I may have to cut a few slides here, but I think this was maybe useful. I will just keep this as is and maybe share it with you then on my video channels here. All right, until next time.